Hello, Science 8. Today we're going to continue on with our physics unit, and we're going to talk a little bit of how light behaves when it hits a reflective surface. And we're going to talk a lot about different devices and pieces of technology that use mirrors in different ways, and just how the laws of reflection kind of allow reflection to happen. So, when light interacts with different surfaces, it can do one of three things. So these are the three things we talked about last week. It can be reflected, so that's what we're going to talk about this week. So bouncing off a smooth surface or a slightly rough surface. So this not only allows you to see a reflection in a mirror or in a lake, but it also allows you to see anything that is visible. So if you're looking at an apple, it's reflecting light. If you're looking at a book, it's reflecting light. So anything that is visible is reflecting some light, just not as much necessarily as a shiny mirror. Light can also be absorbed, like we talked about last week. So something that appears dark or black is going to absorb light. And then light can also be transmitted. So it can travel through a surface that is clear. So something that's translucent, like paper, can show some light, but something that is transparent, like a window, can let a lot of light in. So, reflection. Reflection is the process in which light bounces off a surface and changes direction. So light's going to come at a surface like a mirror and then bounce directly back up into our eyes so we can see that reflection. So if we think of this as a lake, the image of the sun would be reflected in the lake. So the image of the sun comes towards the lake, and then we see that image of the sun back in our eyes because it's being directly reflected off the lake. So I like to think of it a little bit like a bouncing ball. So if I drop a ball of light directly down in front of me, it's going to bounce directly back up towards me. If I bounce it at an angle, it's going to bounce back at a similar angle. The type of surface that light bounces off controls not only how much light is being reflected, but also how the light reflects back. So if light hits a smooth surface, like this gymnasium, you can see that light is visible and it's reflecting back. Versus this rougher surface isn't reflecting as much light back, but we can still see it. So it's kind of bouncing back in a less regular direction. You can think of this a little bit about where would also be a better place for you to bounce a ball. So if you're bouncing a basketball, for example, a high school gymnasium has very nice smooth wood flooring specifically for playing basketball. The bounce is going to be a lot more predictable and come back at a regular angle versus if you're trying to play basketball outside in a bumpy, grassy field, maybe there's some rocks, maybe there's some dirt, maybe some grass, the bouncing back of your ball is going to be a lot less predictable and come back in different directions, but it will still bounce, just maybe not with the same amount of force and with the same level of predictability. So smooth reflection, so this is that we're talking about right here. So smooth reflection, so directly coming back. So when smooth surfaces reflect light, the pattern of reflected rays is similar to the pattern of incoming rays. So reflected rays and incoming rays. So this is an incoming ray. This is a reflected ray. The pattern of them is very, very similar. So they're coming in at the same angle. The fact that they do this so similarly is what allows you to see this image. So when the light reaches your eyes, it's happening in the same kind of pattern as what the light hit the object in. So this happens with shiny objects, with mirrors. It allows you to see an image. Rough reflection. This is a nice contrast to that previous photo. So very smooth water, very, very perfect reflection. This water is a little bit wavier and bumpier. It's showing a little bit less of a specific reflection. So example of a reflection off a rough surface would be paper. So light comes in towards the paper. It's going to bounce off in lots of different directions, which still allows you to see the paper, but it's not going to allow you to see your image or a image reflected in it easily. So the pattern of reflected rays is not similar to the incoming rays. So pattern being that these lines all come in straight and these lines all come off in different directions. So that's how you can tell whether something is a rough reflection or a smooth reflection, is the way the light is bouncing off of it. So some of the reflected rays are reaching our eye, which is making this paper visible, but not all of them in the same kind of way or pattern. So to predict the reflection, we have a couple of laws which kind of guide our understanding of how reflection works and kind of what surfaces it works on. So the angle of reflection is equal to the angle of incidence. So I like to think of this, so if I throw a ball of light down at a surface, it's going to bounce off at the same angle. So the angle, so the distance between this angle and this angle are going to be the same. So when we draw a line there, it means that it's the same. So let's say that this is 45 degrees. This is also going to be 45. I really can't draw with this pen, eh? 45 degrees. So angle of reflection, so this angle here, so angle of reflection, it's got a nice little R on it, is equal, so it's the same as the angle of incidence. So incidence meaning incoming ray, and reflected meaning reflected ray. So that's the light coming in. You can see a little arrow here that's telling you what direction it's going in, and the arrow going out that way. The reflected ray and the incident ray always lie on opposite sides of this thing called the normal. So the normal, if I took and I drew a straight line where my reflecting surface was, the normal is at a 90-degree angle. So 90-degree angle, so it's perfectly perpendicular. So reflected ray and incident ray are always on opposite sides. So I'm not going to get a reflection back from my incident ray coming this way. I'm going to get a reflection on the other side of the normal going this way. But those angles are going to be the same. And then the third law of refraction is that everything's going to bounce off this surface, my reflecting surface. So I gave you a little example in terms of this basketball player. So this guy over here is our incident ray. I'm just going to call it IR because that's what I can draw. And this one over here is our reflected ray, so we can call him RR. And then we can think of this surface, the floor, as that thing that the light, or the ball in this case, is going to bounce off of. And then in between these two guys here, perfectly 90 degrees, that's not perfectly 90 degrees, but I tried, is the thing that we call the normal. Okay, so it's going to bounce directly in the same angle. So this angle is the same as this angle. So if I send the ball off in this direction, it's going to bounce off in the same angle in the opposite direction. So another way you can think of the laws of reflection that I like to think of is a pool game. So if you shoot a ball directly across from you, that ball is going to bounce back towards you. However, if you shoot that ball at an angle, it's going to bounce off at the same angle in the opposite direction. So if shot is made head on, the ball is going to bounce straight back in the opposite direction. If the shot is made at an angle, the ball is going to bounce off at the same angle, but in the opposite direction. So we can think of that again, that normal there, this angle, and this angle are going to be the same. So if this is 20 degrees, this is also 20 degrees. One really cool thing you can do with light is light can actually bounce off multiple surfaces. So just like a game of pool, that guy could hit this ball so hard it bounces off here, and then it could, well, it's probably going to land on that thing. But if you went on a little bit, it could bounce off another surface. So just like a ball, light can be bounced off multiple things as well. And I'm going to show you guys this really cool little video that's got some examples of light, idea of how light can be redirected. Today we're going to talk about 3 different types of mirror. The one you're probably the most familiar with is a plane mirror. So that's a flat surface. We're also going to talk about convex mirrors, which are pointing out this way. So convex, and then concave. So I like to actually think about the cave you would enter. Okay, so concave, convex. So they have totally different results. Plane mirror are extremely flat, smooth, reflective surface. A leak can operate quite a bit like a plane mirror. A window can operate like a plane mirror. What is happening here is light is being reflected by a plane mirror and producing an image that is nearly identical to the object. So light bounces off this guy's head, it's going to reflect into the mirror, and it's happening just like we discussed at that very consistent, smooth angle. It's a plane mirror. So there's no curve in the mirror's surface, so it's going to reflect very easily. However, as you'll notice, if you go into a mirror right now and you stick your left hand up, you will notice that it's not your left hand in the mirror that's, or it doesn't appear to be your left hand in the mirror. It's going to be the hand directly across from you, so it is a reversed image. So this guy's eye, his left eye over here is on the right side. So exactly what's happening is, for example, maybe I have a mirror surface and then I have a candle in front of me. I'm looking down at my mirror at the candle. What's happening is the light from the candle is bouncing off the surface of the mirror, and then it's bouncing off at that same angle as it came in. So let's say this is a 25-degree angle. It's going to bounce back at a 25-degree angle directly into my eyes. What's my eye going to perceive this as? It's going to perceive this as the candle being directly behind the mirror, so a kind of virtual image existing beyond the mirror. But what's actually happening is that the light is bounced off this way. This is just the way my brain perceives this information. Concave and convex mirrors are a little bit more complicated. There are 2 types of curved mirrors. Concave, as I mentioned before, curves inward. So like a dome that you could crawl into. Light's coming in towards this way, so that's our incident ray, the light coming in. It's going to create a different type of effect. A convex mirror is a mirror with a reflective surface that curves outwards. So it's curving like this, a little bit like the letter C. So light's coming in from that way, and it's also going to create a very different effect than this type of mirror. So concave mirror creates very different types of images. So this is a guy sitting in the exact same location looking at 2 different types of mirrors, and we're going to discuss why. So this is largely to do with how light interacts with a convex and concave mirror. When light comes in towards a concave mirror, so you can see little directions of light coming in, they're going to bounce off the mirror. And because they're at an angle, what's going to happen is they're all actually going to meet at this point here called the focal point. So they're being bounced off and redirected. So they're coming in at the same kind of angle, but because of the shape of the mirror, it's going to create that effect. So our reflected rays are coming out towards here. So reflected rays come together or converge at a single point, and that point we refer to as the focal point. You'll discuss this more in grade 11 physics if you decide to take it, but just to kind of introduce you to the specific point where all these light rays are coming towards, and this is going to affect the way our image looks. A convex mirror, reflected rays spread apart in different directions, so they're diverging, so they're going off in different directions because the shape of the mirror is curved. So they're pushing them out in different directions. Concave mirrors, this is kind of what they do for images. So when an object is close to a concave mirror, it's going to be larger. So remember that point I was talking about, the focal point, where all those light rays imaginarily converge. So I can't see that, but I can figure out where it is mathematically. So if my object is beyond the focal point and really, really close to this mirror, what's going to happen is the image on the other side of the mirror is going to be really, really large. This is that virtual image. This is what I see. So I look into a concave mirror, I see a larger image if I'm close to the mirror. If I'm further away from the mirror, so if I take a few steps back, what's going to happen is that image that I see in the mirror is actually going to turn upside down and be smaller. So I'll show you an example of this guy, and there's a video you can watch after if you want to watch him do it. So if he's close to the mirror in front of the focal point, so really, really close to the mirror, I made a little mirror here. So this is him. His head is going to be really large, kind of distorted because of the shape of the mirror. So remember, concave mirror. If he starts backing up, so starts walking away, once he's at this point called the focal point, so the place where all of the light rays meet, what'll actually happen is really interesting. The image is going to start to get distorted. And if you guys were at school, I could try this with you and we could like walk in front of a mirror and watch this actually happen. So then he's going to get distorted, and if he keeps walking back even further past this little focal point that I just told you guys about, so behind that specific point, he keeps walking back further, beyond the focal point, he's going to start going upside down. So what happens, he actually gets bigger, kind of does this warpy image when he's standing on this focal point, and then by the time he's kind of past it, what actually happens with the same type of mirror is he's going to actually go upside down. So you can see how much further along he is. So he's over here now. You could say the focal point is over here. So this is a concave mirror that he's doing here.
My nose in the mirror, then backing up slowly, approaching the focal point, and my image is enlarging. It's getting bigger. At the focal point, the image gets huge, and then just beyond the focal point, you can see the image is still huge, but it's inverted. And then as I move past the focal point toward the radius of curvature, the image is shrinking in size until at the radius of curvature, the image is now unmagnified. The magnification is 1. Beyond the radius of curvature, the magnification becomes less than 1.
Convex mirrors, so mirrors that go outwards, are a little bit less complex than concave mirrors, because concave mirrors have both upright and upside down images depending on where you are looking at them. Convex images, so in convex mirrors, the image doesn't change upside down or right side up. It's always going to be right side up. As you get closer to the thing, your image is going to be larger. So this is our convex mirror. If you're really close to the thing, so this is you, let's come in here, hitting the mirror, you're going to be larger. And then as you go away, you're going to get smaller and smaller.
Start with my nose up against the mirror. It's an upright virtual image. Proceeding out to the focal point, still an upright virtual image. To the radius of curvature, we're still upright and virtual. And then beyond that point, still the same. So it's a little bit more boring than the concave mirror.
Okay, so you guys got to see both, which is great. Again, the links to both of those videos are in the extra resources section. So society and scientists have gotten really smart about how to use convex mirrors. So there's lots of different uses for convex and concave mirrors. So here's some uses of convex mirrors. So what convex mirrors do, because they point outwards, they allow us to see more kind of things in our surroundings. So you can see more objects than you would in a plane mirror. So often you'll see them in stores in security features. So instead of only seeing a small portion of the store, I can see all of this area, all of this area, all of this area very, very easily from this one location, which allows me to prevent people from stealing things and kind of see what's going on in the store if there's only one person at the till. So what widens your view is its kind of purpose. Examples, as I mentioned, security mirrors in school or in stores. Car side mirrors, you want to see around your car up at the back so you can see who's driving behind you. Maybe if there's something over here in the distance. So it, again, widens your view so you can see. And again, those are convex mirrors, so they're the ones that are pointing outwards like domes. So light's coming in like this. And it's bouncing off in all sorts of directions, which allows you to see kind of wider views. Concave mirrors can be used to concentrate light. So you'll see them in flashlights, in headlights. So what's happening there is a concave mirror is round like this. Light's coming in, and then light's going to be spread out in lots of different directions because light's being bounced off kind of to extend. So it's going to produce intense beams of light. We use these things in makeup mirrors to enlarge things. So lots of makeup mirrors have a concave side to make sure that you can see what you're doing. If you don't want to poke your eye out, that's not good. So car headlights, flashlights, makeup mirrors. If you go to the dentist, they would use a concave mirror. Yeah, so its purpose is again to enlarge, or it could be used to redirect light. Here are some extra resources. I would highly recommend you watch the demo of the concave and convex mirror. For today's assignment, or this week's assignment rather. So these are some activities I'd like you to do in terms of reflection. The first activity is a little fun. It's a little game that you can play on Newgrounds, and I'll just show you how it works. And there's a couple of questions related to kind of how the game works. So I'll just show you. So the idea is it's a bunch of different puzzles using mirrors. So this is a mirror here, and then beams of light. There are 25 levels. I've made it all the way to level 25 so far. They start getting really kind of complicated, but I'd like you to play around with it and answer some of the questions. Unfortunately, it's not going to work on a mobile device or phone, so try and see if you can kind of snag the computer for maybe 10-15 minutes to kind of experiment with it. Or it is available on Google Play and might be available in the App Store if you want to try it that way. So there's 4 quick questions on that. And the last question is just to post a screenshot to see how far you got along in the challenge. I'm only at level 25, but it was starting to get kind of tricky. So see how far you can go. The next part is just a couple questions about uses of concave and convex mirrors. And kind of examples that mostly you should be able to find answers to in the PowerPoint. But if you are struggling, you could always kind of look up a little bit of information about why exactly certain types of mirrors are used for certain types of activities. So those are 4 quick questions, just a little 2 to 3 sentence answer is sufficient. And then the last part I thought would be kind of fun. It's technology that uses mirrors. So we didn't talk about tons of things in terms of that. But there's a couple of really interesting things that I think you guys would like to learn about in terms of one-way mirrors. So, you know, when someone's doing an interrogation and there's a mirror in like a police officer headquarters, how do one-way mirrors work in terms of how light's being reflected. The Hubble telescope uses mirrors to see all the way out into outer space. Periscopes, those things you find in submarines. So all I want you to do for this is don't go overboard. But I'd like you to create a little diagram kind of showing me where the mirrors are placed and how the light's being reflected. You can include maybe 3 to 4 sentences about how it's working, but it doesn't need to be super, super detailed. It's just kind of to get you exploring how these things work. Not all telescopes use mirrors, so make sure that you're either looking at a telescope that uses mirrors and maybe some lenses, or looking specifically at the Hubble telescope, because there are some telescopes that only use lenses. Okay, so that's what I'd like you to do today, slash for the rest of this week. And then feel free to come to Extra Help on Wednesday to ask some questions about either this or about the other assignment. Thanks.